All right, guys, so 4.3 is connecting first derivative and second derivative with the graph of f, which is the original function, okay? So we have here first derivative test for local extrema. Remember, we already knew how to find the extrema values from the first two sections. So now we're going to use the first derivative to find it as well. It's just another way, right? So the following test applies to a continuous function. Let's call it f of x. So 1, at a critical point, let's call it C. At a critical point C, okay? So A says, if f prime, which is the derivative, changes from positive to negative at C, then f has a local max at C. Okay, so let's give you a visual. So i.e., it says here f prime, that means it's a derivative, okay? So I'm going to draw out this in this graph right now. I'm going to use f of x. Now it says if f prime changes, meaning that it's gonna be the slope, okay? So would you agree that the slope over here is f prime is positive? Then it changes. That means over here, the slope over here, f prime, is negative, less than 0. So that means at a value of C, here's C, let's just pick that one. This right here, C, so f prime of C is a horizontal tangent, which is equals the slope equals to 0. So as you can see right there, if f prime changes from positive to negative at that location, then f has a local max. So you can see that local max is right there. Similarly to, if I were to give you another example, right, an upside down v, just to kind of make a point. And again, this is an f of x function. So as you can see on the left side, the f prime, the derivative, is positive. On the right side, the derivative is negative. So it's changing from positive to negative. So therefore, this is a max. And that's a max at an x value called C. Okay. Now this derivative right here, f prime of C, does not exist. Remember, the critical point can be when the derivative doesn't exist or when it equals to 0. Now B, if f prime changes from negative to positive at C, then f has a local minimum value at C. And very similarly to the first two examples, right? I'm going to sketch out a regular function, and I'm just going to make a little sketch right there. Can you see that we started with a derivative here, a slope on the left side? This derivative is negative, so it's going from negative to this derivative. This slope is now positive, so it's greater than 0. So you can see here is your minimum, and that minimum value, let's call the x location is C. Okay. And same thing, right? We can say, okay, well, f prime of c equals to 0. Now on the right, similarly to the derivative at c doesn't exist, I can easily make an upside down v, and as you can see, make sure we label this is a function of f, not f prime. Okay, so on the left side, f prime is negative, right? The slope of that's negative. On the right side, f prime is positive. So this is a minimum right here, and we just call it at a value of c. So f prime of c here, students, does not exist, okay? So just like earlier, the critical point can be that the derivative doesn't have to exist, okay? It can be 0 or does not exist. Now c, if f prime does not change sign at c, then f has no local extreme values at c. No local extreme value at c. Okay, so what does that mean when it doesn't change at c? So here's x, here's again a regular function, and I'm going to, okay. Well, as you can see here, the derivative of this particular equation is positive, right? It's positive here, and it's positive over here, right? So, and here it's a c value. So it doesn't change it at all. Because it doesn't change it at all, even though it looks kind of horizontal. Well, my sketch is not as horizontal. Let me make it a little bit more horizontal. Okay, so there you go. Okay, so this is a little bit more horizontal. So again, I'm going to go f prime is positive here, f prime is even positive here. And even though this spot right here, students, looks a little bit horizontal or more horizontal than the right and the left of that, so f prime at c is still horizontal, but because the sign f prime did not change, there's no extreme value at that spot. Now I'm going to draw another example. Okay. So let's see if I can make up a negative one that will make f prime of c does not exist, okay? So again, this is a regular made-up function. Let's do a sharp turn and then a straight line. There you go. All right. So as you can see here, this is sort of f prime. The slope is going downward, so that's going to be negative, and then this is also f prime of this is also negative, right? So here's a funky c value here. Even though, right, the slope on the left and right, they're different, but they're both negative. Mind you, this is just a made-up sketch. So the derivative doesn't exist, but there's no sign change, so it's still not in extreme value location. Now on number 2, let's go over. At a left endpoint, let's call it A. All right. If f prime is less than 0 or f prime is bigger than 0 for all x value that's bigger than a, then f has a local max or min, respectively, value, oh, I can't spell value at A. Okay, what do I mean by that? Left endpoint. So the endpoint's always a bit more tricky. So a sketch. So I'm going to f of x, here's x. I'm going to do left endpoint. So here we go. Okay, can you see that's on the left side of my curve? Well, this is saying that if it's on the left side, and I'm going to do another one that's also on the left side. Okay, so x, f of x, and here's the left side endpoint. Whee, like that. Okay, so can you see that both are on the left side here? We have two conditions here. If the derivative is negative, which in this case it is, right? That is f prime is negative, then this right here, students, is said to be a max, okay, respectively. So now on the right side, it says if the derivative is positive, which is greater than 0, then this point right here, students, is a min. So that's why, all right? And the reason they call it A, because normally we label the graph A to B somewhere. So like A to B, like this, okay? And then C somewhere in the middle. All right, 3. At a right endpoint, call B. At a right endpoint, B. Okay. If, let's draw this. There you go. Okay, so if f prime is less than 0 or f prime is bigger than 0 for x is less than b, then f has a local min or max respectively value at B. So again, I'm just going to do similar sketch to earlier. This is an original sketch, and B is over here, okay, because it's the right end, and it says for x has to be less than that. So that means whatever I have to go wee on that side. And then another one, and here's B. This is an x axis, here's a B, and this y is going to be f of x regular, and like that. All right, check this out. So as you can see, this slope right here, students, that derivative, as you can see, must be negative, less than 0. So if that's the case, then based on this definition, if the derivative is negative, this is the minimum, okay? So minimum is that dot. Now, similarly, remember, and it says here, all of the x values got to be less than b. Well, yeah, because this is on the left side, all of that is less than the value of b. Then the slope over here, as you can see, that derivative is going to be bigger than 0 because the function is increasing. So if that's the case, based on your definition, if it's bigger than 0, then it's a maximum, okay? And that is true, okay? So the endpoints, again, is always the more confusing part for students. Use the graph of f prime to estimate the intervals on which the function f is part A, if f is increasing, or part B, if f is decreasing, and part C, estimate where f has a local extreme value, right? So for the sake of simplicity, can we close this dot up? Let's just say, here we go. And let's close that dot up. Because it's more, I want to practice the closed endpoints here. So now that we have, this is the derivative function. So remember, the derivative function is different from the function itself, okay? So A, it wants us to answer increase, okay? Increase, students, I'm going to write in parentheses here, is when the derivative is positive. And then B, it wants us to answer decrease interval, and the decreasing function is when the derivative is negative. And then it says here, C, estimate f has the local extreme value, okay? So C, local max. Okay, now to get a local max, changes f prime need to go from positive to f prime negative. So f prime has to go from positive negative, or endpoints. am I invading the other side? Or endpoints f prime has to be less than 0 when x is bigger than a, or f prime has to be greater than b for when x is less than b. Remember, those are endpoint definition. Now, how about local max? D, not D, because on part C, the one's L min and L max. Local min is when we have the derivative changes from negative to positive, okay, or endpoints f prime must be positive at a, which is on the left side, or f prime must be negative at b, and remember b is on the right side, okay? All right, so I'm spelling out all the definition for you. So here we go. Increase and decrease. Remember, increase when the slope is positive. So increase, this is positive right here, and this is positive right there, okay? So increase is from -4 all the way to -2. And students, you don't have to use bracket here. You can definitely use parentheses, okay? This one is a personal choice. And then union that with increase could go for, what are we estimating this value? Negative, for the sake of simplicity, can we just say -0.5? So -0.5 all the way to, let's call that a 2. Okay, and that's a closed dot, so I'm gonna have a bracket. And again, on increase and decrease, you can use parentheses, except the endpoint if it's closed, and it has to be a bracket. Now, decrease is when the derivative is negative. So this is negative here, and this is negative here. So decrease, I'm going to estimate this x value 1, 2, 3, 4, 5, -5. So -5 all the way to -4, union that with, and that's going to be -2, and we picked a -0.5 earlier, so I'm going to keep with that. Okay, so that's increase, decrease. So not too bad for increase, decrease. Now, the local min and local max is when you kind of have to pay attention a little bit, okay? The instruction says estimate where, that means x location. So x location for L max would be, remember, we're looking for the changes from increase to decrease, okay? Okay, looking for the change of increase. So here's the increase, and it changed from decrease. So we have the first one at x equals to -2. Then again, or, right? Or we can look at the endpoints. Would you guys agree? Okay, so let's look at the endpoints. The endpoint says f prime must be negative on the left side. Is that a negative on the left side? Or f prime must be, oops, that should have been positive. That should have been 0. Positive on the right side. Is this positive at prime? So both endpoint students are going to be your local max. So -2, 2, and -5. Okay, so those are all L max. Now we're going to go to L min. I'm going to write x equals down here. Based on the definition, we're looking for when the derivative changes from negative to positive. I'm going to erase what I circle here. So this is negative derivative and positive. So the first one is x equals to -4. And then again, here's another one, negative to positive. So the next one is -0.5. So -4, -0.5. And then because we already use up the endpoints as an L max, so that's all we have for that graph. Okay, let's try to go on to this one, guys. So this one, I'm just gonna let it go on forever. Okay, just like that. In decimals, if you don't see that it goes on, if you don't see a closed dot, it does go on forever. On this graph here on the left side, the first graph, I just want to make sure I have an example that has an endpoint. So that's why I wanted you guys to close that up. Okay. Increasing interval is when f prime is going to be positive. Well, looks like the entire thing's positive, except that there's a gap right there. So increasing interval is going to be from negative infinity, take a break at 1, and then union that with 1 to infinity. And then decreasing, students, decreasing is when the derivative is negative. In this case, students, because all of it is already in for increasing, then we just don't have any. So NA or nothing left, okay, for decreasing. C, we want L max, we want L min, oops, L max, L min. Now remember, L max is when we're chasing for the changes from increase to decrease. Well, there was never any derivative change, so there's no L max. Well, we don't have endpoint, so none, okay? L min is the same thing. L min is when we are trying to see if there's a change from a negative derivative to a positive. The entire time, the derivative is going to be positive. So none for both.